We can't hear you if you're talking. You're muted.
Oh, hi. Okay, sorry. Hi everyone. Today we're very excited to have Bodhi today, and he's going to tell us about the light matter interaction in the ZXW calculus, and you can take it away from here.
Thank you. I haven't shared my screen and I don't see an option to do so. Do you need to give me like permission to do it? I can't hear you. You're muted again.
Can you try one more time?
Like, where should I see? Oh, okay. Desktop 2. Is it good?
Yes.
Great. So, hi everyone. My name is Boldizsár, and today I am going to be talking about the light matter interaction in the ZXW calculus. This is a joint work with Giovanni De Felice, Razin, Leah, Harney or Quan Long Wang, and Bob. Okay. So when we know a lot about how to do graphical reasoning about qubits, and now we are learning more and more about what to do with qudits. But what we have been trying to do a lot, but haven't really cracked it properly, is how do we graphically reason about photonic quantum computation? So what is photonic quantum computing? So here we have a different kind of computation. Like in qubits, we have CNOT gates and phase gates. Here we have beam splitters, phase shifters, and other stuff like the Kerr medium. We also have this quantum dot to generate single photon sources. So this is the computation done using photons. It's completely different. In fact, it's so different that the math they use is just, well, to me, quite hard to understand. And that's why they use a lot of calculations using creation annihilation operators and Hamiltonians, but it's just complicated to understand. The math we want to have instead is a graphical language, right? We know the ZX calculus, we love it. It's a great reason about certain things. And also it helps us understand the underlying structure of the physical processes. We know it's really, really good for optimization, and we can also do simulation by just simply writing. And there are also ways to make formally verified software using graphical languages. So one example of a graphical language is the ZX calculus. Its most well-known applications are circuit-based quantum computing. Here we can do quantum circuit optimization, error correction, but it's also really good for MBQC. And there are other kind of calculi too. And one example would be the ZW calculus. So the ZW calculus is different calculus with different applications. It is good to reason about linear optical quantum computing, and we can also express the summation of diagrams very, very neatly in this calculus. And if we put together the ZX and ZW calculi in a single framework, we get the ZXW calculus. And it actually turns out that putting these two calculi together is more than just the sum of its parts. We can do, for example, the exponentiation of Hamiltonians using it in a cleaner way. We can differentiate and integrate ZX diagrams solely within this framework. So it's really a different framework. It's not just the sum of the two. And this ZXW calculus has been applied to do reasoning about qudits, which we like because, well, they are not so nice like qubits are, but they are still quite good to reason about. But when it comes to photonics, the problem is that photons live in the infinite dimensional Fock space. And then there are some equations that are just, they hold in a finite dimensional case, but they are just not even sound in the infinite dimensional case. So one example of this would be the well-known snake or yanking equations. So it's when you have cap and cup, and then you can yank it, and then you get the identity. But this isn't even you can't even express this in the infinite case because it's just not a valid state or a valid diagram. And so that's the problem with the infinite dimensional case. There are just things that are not natural to reason about. And in this paper, our main result is as follows. So if you have this infinite ZW calculus, it's something that you can use to reason about the Fock space. It's where the photons live, sorry. Then you can truncate it into the qudit case, into the ZXW calculus, which is complete. You can do your reasoning here. You can do any kind of reasoning. And then once you are done, you can lift your diagram back into the infinite ZW case. And then effectively what you did is through truncation and lifting, you reasoned about the infinite ZW calculus, why you were able to use those structures that you were not given in the ZW, in infinite ZW calculus. So the structure of the talk is going to be as follows. First, I'm going to introduce you to qudit ZXW calculus, then the infinite ZW calculus, which we use to reason about these photons, and then I will show you the lifting theorem, so this diagram from the previous slide, and how it's actually done. And lastly, I am going to show some exciting applications in expressing photonic Hamiltonians. All right, so let's go. So the qubit ZXW calculus. One natural question you might be asking, and I haven't answered yet, is what the heck are qudits, right? So we don't know what qubits are. They are these two-dimensional quantum bits where any of our state can be in the superposition of ket 0 and ket 1. And then qudits are the generalization of this. So here you have the superposition of ket 0, ket 1, ket 2, and so on up until ket d minus 1. So you have d computational basis states. And you can use all of this to do your reasoning. So obviously it's a more dense way of computing. And in this qudit ZXW calculus, we have the same kind of Z spider syntactically, but the semantics is a bit different because we have a different space to reason about. So the Z spider is going to do what you expect it to do. So it's going to copy the computational basis state. If you input ket k, it's going to make 2 ket k's, right? So this is what it says. If you input k, you get k and k. But we can also reason about phases, right? So we have the Z spider. That what it does, the Z spider, is it corresponds to this rotation matrix. You have any kind of real number alpha, and then you get this EI alpha, so a rotation. We, in the ZXW calculus, use its generalization, the Z box, where instead of any rotation, we get any complex number we want to use, which comes in quite handy when you want to express certain things. But this is qubits. So how do we reason about qudits? So in the qubit case, we have 2 times 2 matrices. In the qudit case, we have d times d matrices. And in the qubit case, you have a single parameter in the Z box. In the qudit case, you have d minus 1 parameter, right? And you put these parameters into the diagonal of the matrix. And then if you want to check, then if d is 2, then this is a 1, a c to the power of d minus 1. So d2 is c1, which is just equivalent to the qubit case. So it generalizes quite well. And if we put the phases and the legs together, we get this formula for one of the generators, the Z box. We have the phases with each computational basis states. You know, this is like a copy in a sense. Then we have the X spider, right? So we have Z and X. The X spider is kind of like an addition. So if you input cat I and cat J, sorry, if you input cat I and cat J, then you get cat I plus J, but we live in D-dimensional wire, so you need to take it modulo D. If it goes up, then it's going to be cut down at the end, just restart the cycle. And then the general formula to express the X spider is as follows. It looks quite complicated, but really what it expresses is the summation of all the computational basis states you put in. And if you have an extra j in the parameter kj, this is like the pi phase. If you have an extra kj, then that just shifts this addition. And we take this whole thing modulo d.
Bodhi, can I ask a question?
Of course.
So could you scroll back when you define the Z box?
Mm-hmm.
Right. So could you scroll back to the other, for this one, can we think of this A arrow as e to the power of minus IZ A arrow? Like, are you basically defining
what you're asking, I'm sorry to interrupt, what you're asking, can we define it for the Z spider case? Yes, in the paper we showed, like, if you do operations element-wise, then you can just say EI and then A arrow, so this A vector, and that's how we define a Z spider in the qudit case. Yes. So.
And is this just a phase gate in the qudit system?
Exactly. Yes.
Oh, so this means matrix exponential can be generalized from the qubit system to qudit system in this way.
What do you mean by, like, yeah, exactly. Yes, we can.
Yeah, because I was thinking the difference between from my opinion of exponential for qubit system versus exponential for qudit system, they differ by the p, where p is the input Pauli operator, and then if you replace the qubit Pauli by the qudit Pauli, and then you replace the theta, which is a 2-dimension, let's suppose you're dealing with a 2x2 matrix, to a d dimension, then I think that's the generalization you're talking about, right?
Yeah, I believe so. Yeah.
Okay. And this is still universal, like everything is still holds when you generalize this?
By universal, you mean can we express anything?
Yeah, using this notion.
So there is one of our previous paper, the completeness of qudit ZXW calculus. So there we have a general normal form for the qudit ZXW. And this normal form just simply expresses any matrix or vector you want to express. So because of that, it's universal. Yes.
Oh, thank you.
Of course. Okay. So we were here, and let's continue. So I said that these kj's are kind of like the pi's in the qubit case, because they correspond to these computational basis states. If you have a kj state, then it corresponds to d minus j computational basis states, and we have a d of these. And lastly, right, we had the Z and X generators, and back again, we have the ZXW, so the last W. So how it's good to think about, it's the summation of diagrams, where it can be used very easily to do summation. So first of all, if you input K0 or cat0, you get 2 cat0s, as the part in the summation shows. And then if you input any kind of cat I, if you input this cat I, you get the superposition of I0 and 0I. So this is what the W does. It gives you the superposition of this thing. And putting everything together, just as a reminder, we have the Z, X, and W. And what you just saw previously is the same thing here. And these are the generators of the qudit ZXW calculus. And they also have rules. So it is in fact a complete calculus. We have rules that deal with interactions between the ZX, then we have rules between the ZW, and lastly, ZXW part of the rules. Don't try to understand these things too hard. I'm going to a bit later go into details in the next part of our presentation, the infinite ZW calculus. So the way you should think about it is this kind of a generalization of the ZXW calculus, but to infinite dimensions. And so you don't see the X, but it will have something corresponding to the X, but not exactly, because it's just not well defined. So ZW calculus, we use this to reason about the Fock space, and the Fock space is where photons live. So this is, linear optics or any kind of photonic systems you can reason about. And in a wire, the state is a single bosonic mode, which is the direct sum of any number of photons. So this means that we can have in a wire 0 or 1 or 2 photons and so on up until even infinite number of photons. And then an important restriction we have is when we are talking about states, they need to have a finite support. What this means is that there must be finitely many non-zero terms in a state. In the paper, we use the category vec10 to reason about these things. Its objects are the finite tensor products of this single bosonic mode, and morphisms are linear maps between them. And then let's talk about the generators. So we have the Z node. This is a direct generalization of the ZXW calculus. The only there are two differences. So the first is that here, instead of having a D, I hope you can see my cursor. So at the top of the sum, you don't have D-1, but you have an infinity, because you have infinite number of computational basis states, but everything else stays the same. And the other subtle difference is that the phase is now an infinite vector. And then what I told you previously about is this restriction that our states must have a finite support. So this is a state because it has no input. And what we are writing here is that the phases of this vector must be so that there is a finite n, such that after that n, all the other elements are 0. So what this means is that after this n, there is no more computational basis states coming in. So this is a finite state, right? And then we have the W node, again, very direct generalization, but instead of D-1, we simply write infinite on top of the sum. And then again, we have this cat I is mapped to I00 plus 0I00 and so on. And so this was Z and W. the two nodes we saw. And then we now have also bosonic nodes. This one is called the split, and this is the merge, because if something comes in, it splits it, and this one merges it. And this is the generator that kind of corresponds to the qudit X spider. And why? It's because let's look at the merge map. So if you have n and m, two computational basis states coming in, then what you get is n plus m. So, right, you get the sum of the two. But now we are in infinite dimensions. So in the qudit case, if you remember, we took it modulo d, but now d is infinity, and modulo infinity is the identity, right? So that's what I mean by a generalization. It corresponds to the X spider, because we have the summation modulo infinity, which is just the identity. And then the other difference is that it has a phase, which is important if you want to reason about certain optical instruments like the beam splitter. And lastly, we have n photon states and effects. So these are just simply, you have a state and you initiate n photon, like you have n photons there, and that's going to correspond to ket n. And you can also measure, and if you measure n photons, it corresponds to bra n, and these are these states and effects. And the ZW calculus, the infinite ZW calculus, has some axioms just as well. They are, in a sense, again, generalization of the qudit ZXW calculus. So here we have, for example, the usual fusion of Z spiders. We have some algebra between the W node and the Z node, and then the W is symmetric and associative, and there are some other things. I don't really want to go into detail here. It's well explained in our paper if you are interested in the detailed explanation. We have rules from QPath. So QPath is a calculus introduced by Giovanni and Bob from 2022. Is using these bosonic nodes, and they can reason about linear optical phenomena. And here are a subset of those rules that we need to use. And then there are some interaction rules between these generators. Now let's go into the main result of our paper, the lifting theorem. So just a reminder from the beginning of the presentation, what is this lifting theorem? So what we say is that we can, oh, hi. Sorry, I heard someone.
Sorry, I think it was me. Just ignore me.
Okay. So we can now know what infinite ZW calculus is. So if we have some diagram, we want to do reasoning that we naturally wouldn't be able to do in here, we can truncate it into the ZXW calculus, which we know is complete, so any equation can be derived. And then once our reasoning is done, we can lift it back. And one thing I didn't mention previously is that this has some kind of restrictions when can be lifted back. We can only lift it back if the states are well defined in the ZW infinity calculus. So states with infinite support are can't be lifted back. And that's how we do the reasoning. If you want to do some reasoning in ZW, truncate it, reason here, and lift it back. So first, what I'm going to explain from this diagram in a bit more detail is the truncation. What kind of, what is this? So the truncation is this t or tau d, which maps from ZW infinity to ZXW d. And one thing that's important for us to express this truncation is this projector on the d particle sector. So what does this do? So if you input two computational basis states, it's going to act as the identity if the sum of these two computational basis states is less than d. So say your dimension d is 3, and you input cat2 and cat2, then cat2 plus cat2 is 4. 4 is bigger than 3, so it's going to be the zero diagram. So it doesn't, like, it maps it to the zero diagram. But again, if your d is 3 and you do cat1, then you have 1 plus 1 equals 2, so it's less than 3. So it's going to be just the identity. And we can actually express this d particle sector projector as the following ZXW diagram. And one thing I should mention here is this n is just the vector 1, 2, 3, 4, 5, d minus 1. And every operation is element-wise. So what we do with this truncation operator is if we have a z node in the infinite ZW calculus, if we truncate it, we are just going to have the phases cut down at the given dimension, and everything else stays the same. The W node is mapped to the W node quite naturally, but just be aware this is the infinite version and this is the ZXWD. So this is the dimensional version. They are not the same, but this is the truncation of this. And there are the bosonic nodes. So if you remember again what I explained previously is that this is the split. The splits and the merge are rather similar to this X spider, and kind of this is how we do the truncation as well. So what I said is the difference between the X spider. One of the difference was the phase. So these ones have phases and the X spiders on, and these Z boxes are the ones responsible to represent these phases. And then the D particle selector is what is responsible for not overflowing this mode D, right? If you have something bigger than your dimension, then it shouldn't overflow into cat1 again, but rather it should just give you the zero diagram. So this is how we express it. And the merge map, it's just the transpose of the previous. Okay, and the last thing we have were these n-photon states and effects, and they just simply correspond to cat n. Sorry, I have a comment.
Yeah, can we just
No. So they correspond to cat n and bra n as needed. This truncation is sound. So what does this mean? It means that this diagram or this rectangle commutes. So if we start from the infinite ZW calculus and we truncate it to the qudit ZXW calculus and then interpret it into qudits, it's the same as first going into the Fock space and then truncating it. So this TD truncation is sound because this diagram commutes. And now maybe the most complicated, but the main result of our paper is the lifting theorem. So here, feel free to ask anything if you feel a bit stuck, because this is a very, very loaded theorem. It even though it's so small, it's just it takes a bit of effort to understand it. So let's try it. So if you have diagrams in infinite ZW, and you know that their interpretation is the same in the Fock space, so you have two diagrams and their interpretation is the same in the Fock space, then this is equivalent to the following. So for any, if we restrict the inputs to only n number of photons, so here just a quick notation, this is the n number of, like here, this means that there can be only n number of photons coming in. It's the same as the d-dimensional, but now we can set it to be n. Okay, again, so if you restrict the input to be n photons at most, then there is a large enough d that the truncation of the above diagrams are equal. And for all d large enough, this is going to hold in this n particle subspace. So again, if you have two diagrams and their interpretation is the same in this Fock space, then this is equivalent to being like for any number of photons, at most that many photons coming in, their truncation is also going to equal for any d which is bigger than a given d star. Okay, just giving an extra moment to take a look at it. Hope everyone is fine with this. So in the paper, we don't just say that there exists a d star such that this holds, but we also give you an algorithm to find this d star. So what we are going to do here is, so first of all, we will kind of show how many, so we are going to slice up this diagram and then we go through the whole thing, consuming it one by one. And we are going to just increase this d star based on at most how many photons there can be at the diagram at the given time. So first of all, when we start with this projector, d star can be set to n+1 because after this projector, there can't be more than n+1 photons. And then the bosonic and the W nodes are particle number preserving. So what it means is that if we don't need to increase this d star because they can't change the number of photons. Naturally, if we have a k photon state, it increases our maximum number of photons by k. So after this, the d star will be set to d star plus k. And then the one where we have maybe the biggest assumptions are the z nodes, where, so before the z node, it was d, the maximum number of photons, and after it, the most number of photons that can come out after this is m times d, where m is the number of outputs. But here, so what we do is just give large assumptions so that the theorem we gave previously holds, but this is not an optimal number of, a minimal number for d star. So you can definitely find smaller d stars such that this holds. If you would like to do simulation using this method, then you would probably want to find some d stars so that it's minimal. And then, what can we do? So now we have the lifting theorem, right? Which means, maybe I can quickly show it, which means that, okay, whatever. Which means that we can reason about the ZW infinite calculus within the ZXWD calculus right? So we can first have some equality, and then if we are here, we can truncate it, right? So the truncation of the merge node was as this. And then we can do our reasoning in the qudit case. So these steps hold. If you want, you can check. And what we get after going through this proof is that this ZZ and then the split map and W is equal to this map, where we have, again, the same thing, but now here we have two W's as well as a projector. And then, so we have this equality in ZW infinity, we did the reasoning in ZXWD, and now we can lift this result back into the infinite case to get the above equality. Someone might realize that in the proof we have two of these projectors on both sides, and in fact we can actually put projector on both sides of the equation, and then two of these equals just one because it's a projector, and that's how we get the equality. Right, so what we just did here again is we reasoned about infinite dimensional Fock space using equalities in the qudit case. And in my opinion, one of the most exciting parts is reasoning about photonic Hamiltonians. And why am I saying this? So if you have worked with Hamiltonians, then you probably saw Pauli's, right? But what's happening is in quantum chemistry, they have these molecules and they are described by actual photonic Hamiltonians. And then they use certain algorithms to convert these into these Paulis that we all know. But if we can do some optimization in this photonic setting, then it's going to have such a drastic effect because they are just mapped into other kind of phases in this Pauli phases or Pauli Hamiltonians, which are much more complicated. So what do we have here? So first of all, what I want you to understand to have reasoning here are the control diagrams. So we say that a diagram is a D is control is a for diagram D, a control diagram D tilde is just a diagram so that if you input 0 on top, you get the identity. And if you input 1 on top, you get the diagram, right? So if you input 0, you get the identity. If you input 1, you get the diagram. It's quite simple. And then we can express in our language the controlled sum of these control diagrams. So if you want to express the sum with some phases, if you want to, then you can express it with a W, because the W is going to express the summation of ket 1s, and 0 goes to 0. So if you input 0, you get 0, 0, 0 everywhere, resulting in the identity. So this is in fact a controlled sum. And if you input the 1, then you get the summation of all these diagrams. And we can also express product, the controlled product. So if you input here 0, you get 0 everywhere, resulting in just identity. If you input 1, then everything is going to be 1. So you get the product. And another thing that we will need to do the reasoning are the creation and annihilation operators, the bosonic ones. So the controlled creation operator is actually just the merge map, and the controlled annihilation operator is the split map with a cup. And an interesting thing that we can prove is the bosonic commutation relation, which is as follows diagrammatically. It just says that the commutator of A of the creation and annihilation operator is 1. This is how it's expressed. It's, in my opinion, very, very neat. And it has a very cool proof too. And then we can also express the fermionic creation and annihilation operators. So the controlled creation is just the W node, and the controlled annihilation is just, again, the W, but the other way around with a cup. And again, we can express the fermionic commutation relations as follows diagrammatically, and we can prove it using just diagrammatic tools. And lastly, the interesting part is to actually express linear optics. So if you have done some photonics or optics, you are probably familiar with the phase shifter or phase shift. And the Hamiltonian of this operator is given as follows. So some alpha times the annihilation and creation annihilation. And if you put together the previous slides, sorry, I have presentation. If you put together the previous slides, then you get the following diagram. And then in the ZXW calculus, you can exponentiate it. And then you can prove that the exponent of this is just e to the I alpha n, where n is again this 1, 2, 3 vector. And similarly, you can express the Hamiltonian of the beam splitter, which is given as follows. And you can show that exponentiating this, and that exponentiating this gives the following diagram, which is the beam splitter. So this is what people use, like these two, the phase shifter and beam splitter, are the basic components of linear optics. People use these two things and they can reason anything within linear optics. But we also have something called nonlinear optics, where we have a nonlinear nonlinearities in our Hamiltonians. So another thing I quickly want to mention is that linear optics is not universal if you don't have post-selection. So it's only universal once you have post-selection, which in a sense gives you nonlinearities. But what you need to do a universal computation is to input some nonlinearities into your systems, and nonlinear optics is what you can use to do that. And one example for such an instrument would be the Kerr media, which is expressed as the following Hamiltonians. It's just the Hamiltonian is simply the product of two phase shifters, but then exponentiating it, you get e to the I kappa and then n squared. So this is where this nonlinearity comes in. And then there is the cross-Kerr gate, which is an entangling gate, and is given by the following Hamiltonian, and exponentiating it gives you, oh, sorry about this, but exponentiating it gives you the following diagram. And here's something interesting. If you look at it, this W node was just like the X spider, right? Or this merge node was like the X spider. And what these green phases do is they just cancel the phases. So this is very much like an X spider here. So how you can perceive this is it's like a phase gadget with very interesting phases. And then you can prove that two cross curves after the other is just the sum of the, it can be expressed as one bit where you sum up the parameters, and the proof is just exactly or almost the same as how you prove the addition of phase gadgets. And lastly, there are two things I want to mention. There are some much more complicated Hamiltonians you can express in photonics. One of them is the Jaynes-Cummings. And so here, if you remember, we had bosonic and fermionic nodes. Bosonic is like light, and then fermionic is the matter, and this is where the light matter comes in. So this Jaynes-Cummings Hamiltonian expresses the light matter interaction. And this is how we can express it in our language using this diagram. And there are generalizations of these Jaynes-Cummings. This is called the Travis-Cummings Hamiltonian, where you have any number of modes with the following relations. And this is it. So what I quickly want to mention here is what kind of future works we have in mind. So one of the interesting things we started looking into is how do you express and how do you reason about sources of loss and classicality in photonics. So in photonics, one of the nice things is that error is maybe a bit better than in qubits, but you still have photon losses. And how do you express this photon loss? Continuous variable quantum computing. So here what we did was reasoning in the Fock space. But there is the continuous variable setting where you can reason about even states that doesn't have a finite support, but still has some restrictions. But generally speaking, this is a different way where you can do reasoning using the momentum and position. We are looking into how we can reason about reason in this setting. Another interesting thing is in understanding different properties of Hamiltonians diagrammatically. And then lastly, the classical simulation of photonic systems would be an interesting avenue to chase. And with this, I thank your attention and feel free to ask any questions.
Thank you, Bodhi. So does anyone have any questions for him? So may I ask a question about the controlled operation? Could you go to the slides?
Yeah. Which one?
I think it's when you first introduced it.
Okay, here.
Yeah. Would you mind reminding me this 0 and 1? Like, is this like the 0 control, 1 control, or?
So 0 is the computation. It's like the X spider with no phase, and 1 is like the X spider with a pi phase. So this is cat 0 and this is cat 1. And this is how we define a control diagram D tilde. If you input the computational basis state 0, right? Then you get the identity. And if you input the computational basis state 1, you get the diagram. Is this clear?
Yeah. So this notation is defined for a system of one type of dimension. So this means the control qubit and target qubit, they're in the same system.
Sorry, could you repeat?
Oh, yeah. So I was wondering, is it possible to generalize this notion to define a qubit controlled qubit gate? Basically, you have a mixed system.
I see. That's actually a very interesting question. Yeah. So there is in the frameworks you have seen throughout this presentation, you cannot do this because all the wires have the same dimension, D, or infinite, for that matter. And we have with Harney a paper recently put on arXiv where the qfinits at W calculus where we prove it's complete. That kind of frameworks can be used to reason about different dimensions mixed into a single one.
Oh, okay.
Yes.
Thank you.
It's actually very
Michael, please go ahead.
Yeah, I'll try to formulate this in a useful way. This is more coming from my background in physics. So one of the things that you always look for in sort of these kind of, and of course, these kinds of models is physicists love coming up with finding exactly solvable models. So ones where you can actually do things much more simply. And I was wondering if there's any sort of possibility of using these tools to sort of have a diagrammatic interpretation of that, so those sort of things.
We haven't thought about it, but it definitely is a very, very interesting way to go through. Yeah, simply we haven't thought about it, but I do believe it's possible, and it would be quite interesting to see how it would look like here. Yeah, thank you.
Hi, Bolly. So I missed the first half of the talk, so apologies if it was already answered in this first half. You mentioned that like this exponentiation, that you can do this in the calculus and then you get this order diagram. Is there like a neat diagrammatic proof of this once you do this? Like you have this, you write Hamiltonian and say, well, if you exponentiate it, you get this like very simple diagram. Is there some easy way to see this?
No, I think personally, I feel like that's like one of the trickiest part to do, because it's a very tricky way to express these things. We definitely would benefit if we had a nicer way to do this. We try to express this in a way that it's exponentiatable in a sense, and then do the reasoning after that's done. So the exponentiation is not expressible neatly diagrammatically, but it is possible through going back to the Hamiltonians.
Mm. So you're using this outside information at all? Well, you know what the Hamiltonian is, so we know the exponentiation should be.
Yes, in a sense, yes.
Okay. And could you go to your slide where you talk about the Kerr effect and that this was like a phase gadget?
Oh, the cross Kerr, yes.
Yeah. So I just want to point out that you say this is a phase gadget, but it's more like a controlled phase gate, because this is exactly, if you decompose a controlled phase gate in phase gadgets, you get this central phase gadget, but you also get the phase gates on the top, and they have like a negative sign compared to the positive sign in the middle. So this is together, it's like just a controlled phase gate.
That's
right.
right.
I guess, does that make sense based on Hamiltonian? I guess it does, right?
Mm-hmm. Yeah.
Yeah.
Nice.
Okay.
Thank you.
I have a very naive question. It's in the definition where I think you listed all the relations, and I saw there's a notion of large scale quantum computing with ZXW calculus there.
Notion of
like large scale, like you have this like similar to a rectangular shape stuff, like it's earlier when you introduce the notation.
Sorry, where the notations of ZXW calculus, or
A bit later. Later.
The infinite ZW calculus.
Bit later.
Bit later.
Next. Yeah, here.
Okay, I see.
On the bottom right, is that like the large scale notion for
this one?
Yeah.
Oh, no. So this is in the completeness paper for ZXW. It's nothing to do with large scale. So here, this V box, we were a bit cheeky here, because this V box expresses something very similarly sized as this one. So this has actually the same kind of complexity, but no, here we have just like saying that if you have this many wires with these specific phases, then they can be merged into a single Z node, Z spiner, Z node. So this has, sorry, yep.
So what do you mean by this shape with numbers in there?
So I see what you mean, the multiplier, this gray 1 and -2. So it is just a green box, a green spider and a red spider connected with the number of element, like the number that is represented here. So for example, this d-1 here would be this with d-1 written there, right? And then if you have k wires between the green and the red, then that's going to be k. It's what it's going to do, it's called a multiplier, and it's going to multiply your computational basis state with k, if k is the value on this multiplier.
Oh, interesting. This reminds me of Guinness album, where it's also like multiplying the input qubit, but maybe it's a different thing.
What does it remind you of? I didn't quite get
Guinea adder, like Guinea elbows. So Greg Guinea decomposed like Toffolies into left elbow, C0, and right elbow. And then like this left elbow operation also performed the multiplication. But I'm not sure how these are.
Is that for qudits or for qubits?
No, this is just for qubit.
Right.
Yeah, but that's very interesting.
It is very interesting, definitely, yeah.
Thank you.
Of course, yeah.
So last call for question. Does anyone want to ask Bodhi some last minute question? Alex just joined. Hi, Alex.
Hello.
You're late to the party.
Not that late, I hope.
Do you have any questions?
I think Alex didn't realize that it was an hour earlier today.
Oh, yeah, this I completely didn't realize.
We should have sent out another reminder. Sorry about that.
Yeah, so
but
my
we recorded.
was this talk very similar to what Rosine talked about in Oxford the other day?
Yeah, exactly. Yeah, so you didn't miss new information here, yeah.
I'm not too sad, but I'm sure you gave an excellent rendition.
So since our chair is here, I'll just ask John, what should we do now?
Well, I think there's no more questions. Well, it's been an hour, so we can call it a day.
Yeah.